We present a novel numerical method for form finding with constraints and objectives. Form finding is a technique to find a structural equilibrium for given boundary conditions. Numerical method of form finding allows to take into account various complex constraints. This project illustrates such an example, in which the planarity of the facet is imposed while the shape is found the closest possible to a pure compression structure. Like in this example, often the design constraints have conflicts with desired structural equilibrium. Numerical methods allow us to find solutions that satisfy both constraints. However, there may be an infinite number of solutions for given constraints. This presentation is about how to choose a unique solution among infinite possibilities. The proposed method is based on a so-called constraint projection. Constraint projection is used to find a solution which satisfies multiple constraints through two-steps optimization. At the first step, a solution for individual constraint is computed, which in this example is the planarity of a distorted quad. At the second step, local solutions are integrated into the global solution. Iterating these two steps converges to the closest solution which satisfies all the constraints. The central idea in our method is to decompose the global equilibrium into a nodal equilibrium and treat it as another type of constraint. The integration of local result back in the global system makes the state of iterate closer to the equilibrium. The advantages of our method are its extensibility, robustness, and performance. Extensible. The method does not require the derivatives of the constraints. Therefore, various nonlinear constraints can be easily incorporated in form finding. Robustness. Even with a poor initial condition, the method can converge to the intended solution if the right constraint is given. Performance. Each constraint can be efficiently solved in parallel. An acceleration technique can be used in order to boost the convergence rate. Our contribution is the application of the objective function in form finding. Often, the problem is either underdetermined or overdetermined, meaning that either there is not enough constraint to determine a unique solution or there are too many conflicting constraints which cannot be simultaneously satisfied. This simple example is an arch of semicircular shape. Obviously, semicircular shape and pure compression of the arch are two conflicting constraints. In this case, semicircular constraint can be relaxed and set as an objective target instead of hard constraints. This problem reformulation allows for finding a unique solution that minimizes the discrepancy to the desirable shape. The objective function can be straightforwardly inserted in the original formulation of constraint projection. This approach can be applied to more complex problems with combined tension and compression members. In this example, variable member lengths are prescribed in function of the distance to a specific point. The length constraints are given as objective function rather than as hard constraint, which do not have to be exactly satisfied. In this way, the user can manipulate the resulting shape without compromising the other hard constraints which are given the priority. Another example is the form finding of a grid shell with planar quads. The first example shows the result with only equilibrium and planarity constraints. This solution is not practically interesting, since the mesh is found slightly distorted in order to satisfy the given constraints. In the second example, mesh smoothness is applied as objective function along with other constraints. This resulted in a smoother mesh definition which might be practically preferable. In the third example, soft constraints on the member lengths are prescribed such that they become larger towards the center of the structure. By setting different objective functions, the user can explore different solutions. The method is applied to a pure compression shell structure with a tension ring. The first example shows the form finding with the circular edge as geometric constraint. Although a solution is successfully found, the edge is distorted in elevation, which might not be preferred from an architectural point of view. The second example is made with planar edge constraint. However, the mesh is slightly disturbed in order to satisfy the edge planarity. In the last example, mesh smoothness is applied as objective function. The regularity of the mesh is clearly visible. Interestingly, the tension ring turned out rather a triangular shape. We presented a novel approach to form finding with constraints and objectives. With the proposed tool, the user can explore a design space and find a unique solution that satisfies the architectural requirements which are specific to the project. For those who are interested in detail, the further discussions about the formulation and the implementation of the method can be found in the conference paper. Thank you for your attention.